Hello everyone, welcome back to my channel. I hope everyone is doing great. My name is Ravi Teja. So I've started solving dynamic programming problems from the study plan which was created by Leetcode. Okay, so I've already uploaded video related to climbing stairs. Let's solve the Fibonacci number today. Okay, so let me jump back to my iPad and I will start explaining you what what are we trying to solve. Okay, so the problem statement states the Fibonacci numbers, commonly denoted by f of n, forms a sequence called the Fibonacci sequence such that each number is the sum of two preceding numbers, okay, starting from 0 and 1. Okay, so if you see, the Fibonacci series has two base elements, okay, 0 and 1. Okay, it has as per the problem statement. Now the next number will actually depend upon its previous two numbers. Okay, so this number is derived by adding this number and this number. Okay, so 0 plus 1 is 1. Now in order to derive this number, I have to depend upon previous two numbers, which is 1 plus 1, which is 2. In order to derive the fourth Fibonacci number, okay, I have to rely on its previous two elements, which is 1 plus 2, which is 3. And in order to derive this, I will be depending upon these two, which is 2 plus 3, which is 5, and so on and so forth. Okay, so let's not look at the recursive relation which they have given to us. Let's try to derive it. Okay, if I am at an index I, how can I derive this particular number? Okay, as per the problem statement, it will always depend upon its previous two numbers. Okay, so this is formed by f of I minus 1. Let's say f is the function which will tell me what is the ith Fibonacci number. Okay, in the Fibonacci number at the ith index, where I am starting it from 0. So f of I will basically depend upon I minus 1 and I minus 2. So f of I minus 1 plus I minus 2 will be the I minus f of I for I greater than 2. Okay, so for 2 and above, this relation holds true. Okay, whereas for 0 and 1, okay, when I is 0 and 1, there are no more elements which it can previously depend upon. So these two cases I have to define it exclusively. Okay, so we have to look for the I values wherever recurrence relation does not holds true, and we have to define them explicitly. Okay, so for I less than 2, f of I is basically I, so that is what I have defined, right? So before implementing this recurrence relation directly, let's try to look at how the tree diagram will look like. Okay, so f of I is depending upon I minus 1 and I minus 2. F of I minus 1 is depending upon f of I minus 2 and f of I minus 3. And f of I minus 2 will depend upon f of I minus 3 and f of I minus 4. Okay, if you see, there are problems which are actually repeating, okay, sub problems. So if I have computed answer for this, then I don't have to compute the answer over here. If I compute answer here, I don't have to recompute it again, because answer will always turn out to be the same, right? So instead of recomputing answers which were already computed, okay, can we do anything better over here? So we will be caching those values and we will be reutilizing whenever it is required. Okay, so that is where dynamic programming comes into picture. Okay, so let me jump back to my Leetcode and try to solve this problem. Okay, so as I mentioned, I have defined a function which will depend upon these two. Okay, let's have a function, let's say, which will find Fibonacci series, Fibonacci number, which will take I as an input, right? And it will simply rely on its previous numbers, right? Fibonacci number of I minus 1 plus Fibonacci number of I minus 2. Okay, now that I have coded this particular part, now I should also include the base case. So the base case is when I is less than 2, I should return I, correct? Now let's try to call this function. Okay, Fibonacci number of n. Okay, So let's try to run. As you can see, base cases were passed because n is pretty low. Okay, so this is simply recursive relation. Okay, I haven't done any memorization or nothing. Okay, now it is recomputing the results which are already computed as I've shown here. Okay, so let's try to memorize it. Okay, so in order to do memorization, I will keep an array at my class level and I will instantiate it. Okay, with size of n plus 1. Okay, now I will basically fill it with -1, so that I will be knowing that if dp of I is -1, that means the value is not calculated yet. Okay, so what I will do, if dp of I, if it is not equal to -1, that means answer to it is already calculated and I should simply return it. Okay, or else I will be computing the answers and I will be storing it in my particular dp of I. Since this array is at class level, this function will also have access to it, so I don't have to pass it over here. Okay, so let's try to submit this problem, run the problem and see what all the base cases were passed. Let's try to also submit this. Okay, as you can see, all the test cases were also passed and it is pretty efficient solution in terms of time complexity. Okay, if you see, the overall time complexity is we are just populating the dp array, okay, which is of size n plus 1. So the overall time complexity will be big O of n, and space complexity is also big O of n, where we are actually calculating, we are storing all these values. Okay, so let me also show you this approach is called top down approach, where we are calculating the sub problems solution and then we are relying on it. Okay, so bottom up approach is basically where we will solve the smallest problem which is possible. Okay, and then smallest problem which is possible, and then we'll try to solve the problems which are just bigger than it. Okay, so we will be populating the dp array in this particular format itself. Okay, so let me just, since dp array is already defined over here and I don't have to redefine it. Okay, so what I will do is I will just iterate from 0 all the way till n, and then what I have to do, I'm just converting my recurrence relation into bottom up approach. I'm just showing you how I can do it. Okay, it is simple, right? So when I is less than 2, okay, when I is less than 2, I should fill my dp of I with I, or else I have to fill my dp of I with dp of I minus 1 plus dp of I minus 2. It's as simple as this. I just converted this into this. Okay, in the end I have to return dp of n, right? So let us call this function over here. Okay, bottom up of n. Okay, so let's try to run this problem. As you can see, base cases were passed, and let's also try to submit this, and you will see all the test cases will also pass. You see, now that both the time and space complexity are like in the bottom up approach, what we are doing is we are skipping the recursive calls, and the space required by the recursive calls will also be reduced. Okay, so if you see, okay, if you keenly observe, we can also reduce the time complexity, we can also reduce the space complexity from big O of n to constant space, because at any given point it is only relying on two of its values, the previous value and the value previous to it, right? If you know the previous one and previous two, that is all it requires, right, to compute the current value. So I will just give you this as a homework for you to optimize this. Okay, and that's all about this problem. I've seen people consuming my videos but not subscribing to my coding channel. I highly recommend you to subscribe so that you won't be missing the content which I am posting on daily basis. Let's upskill ourselves together on daily basis and Hit the like button, hit the subscribe button, and share your valuable feedback in the comment section. That's all about this problem. Thank you.